Welcome to Physics 105. Today we'll continue where we left off on Monday. Basically, I'll try to solve some examples from your book, and if we have time, maybe some of the suggested problems. And let's see. So maybe I can share my screen. All right, that's very good. So let's go ahead and start then. It seems like there's no question. Just to remind, we are on chapter 4, dynamics, Newton's laws of motion. So what did we do? We talked about force on Monday and Newton's first law. We talked about mass and Newton's second law, F is equal to ma. We talk about Newton's third law. For every action, there is an equal and opposite reaction. These action-reaction force pairs. And we talked about weight, force of gravity, and normal force. And I think we solved 1 or 2 problems. Today I want to, okay, this is the one we solved, this one we solved. Maybe today I can start from this guy and continue, okay? So a window washer pulls herself upward using the bucket pulley apparatus shown in figure. So basically, she's standing in a bucket, and bucket is tied to a rope, a string. String goes through a pulley, comes down, and she's pulling herself. Okay, that's the setting. And how hard must she pull downward to raise herself slowly at constant speed? Okay. I'll give you a couple of minutes and let's see what you guys think. Let me just wait until I see a couple of answers in the chat box. So she's standing in a bucket. Bucket is tied to a string that goes through a pulley, comes down, and she pulls herself. And you want constant speed up. Okay, I have one answer. I have another energy, 706, 710 Newton. When we do these things, I really recommend you have your pen and paper ready. And please, you'll like overwhelm the inertia you have that resists to you do anything. Just take your pen and paper, start writing a few things, test it. If you are confused about something, it is very likely many other people are confused about the same thing. So ask it, don't be shy. So I have about 2 different groups of answers. One group is 710 Newton, the other is 350 Newton, okay? I think we have a fair amount of people thinking it's difficult, and that's fine. Okay. My suggestion is if you identify a difficult problem, I think it's good for you because you identified something you should work on. Okay. So let's just start. And so maybe a few of you can write, what is difficult about this problem? If you think it is difficult, what is the most confusing part? So I look at the problem and I think, okay, this problem is difficult. But just saying it's difficult, so okay, it's tricky for beginning, yes. There should be an option of somewhat agree as well, I think. Okay, maybe next time, I think that's a fair demand. Maybe I can next time agree, disagree, neutral. Yeah, that's a good point. So I look at the problem and I say it's difficult, but that doesn't help me. I now want to go a little bit further and say, okay, what is difficult? Let me identify the part that I am having struggle, okay? Which part should I focus? What is the most confusing part? Come on, write 1 or 2 things, just as for speculation. It doesn't have to be like a very deep answer. Equating the equation is what I find a bit tricky. Yes, generally it is setting up the equations and looking at the equation, right? So we can first start with setting up equations. Tenses on the rope pulls her. Okay. Both ways. Yeah. How does she pull? Okay. Pulling herself is the part that's confusing. Okay. That's fair. Anybody else? How tension works in this equation? Okay. So tension, how she pulls. Okay. Let's start with what she does. What she does is to pull, right? Let's zoom in just a little bit and look at her. So, okay, am I good here? Yes. So what she does is hold the rope and pull, right? This is what she does. That's the force on the rope by the woman. Okay? But we are interested on the forces on the woman. So if she exerts a force on the rope, Newton's third law says there must be an equal and opposite force, like this, right? Maybe I can write these forces. So so this woman pulls it. This is force on woman by the rope. But Newton's third law says for every force, there is an equal and opposite force acting on the different object. So then this woman experiences a force like this. This is force. Okay, sorry, I messed up. So this is force on rope that she pulls on rope by woman. And this is force on woman by rope. Okay? And so let's just use our intuition a little bit. So imagine you are like pulling a string, right? And of course you pull, you know the force you put yourself, but also think about what the rope does it, right? The rope kind of lifts you, right? So the force is supposed to be up. So we don't have any problem with this. Does anybody have any problem with this? Okay. Now I want to call this, let's call this, I don't know, T, because I don't want to write this FWR every time. So if I follow this rope, so it should balance, right? Whatever tension is here should be also here. Then I'll just do that. This force on the rope, like this, I'll call this T. And where does this force act, right? Where does it act? I can see it is acting on the bucket here. And this bucket as a whole system is, I can put like a black box and connect everything here. I don't care what is inside, but it is pulled by here. There are two, so this whole object, if I look at it, there are two pulling points. One is here, the other one is the hand of the woman. And the problem is, let's look at the problem. The problem is saying mass of person plus bucket. So we have to look at the whole system. So what other forces do I have in that system? Obviously, I have gravity, so I will not wait for you to answer that because I think all of you guys can see this, like this. Oops, that's a little bit, okay. So this one, mg, okay? Now, I can probably set the equation. So let's say A, Newton's second law, sum over all forces, and we are looking at the y direction. Just make sure, let's make sure we just note it, Fy should equal to m times A. Okay, now I look at this equation and I ask myself, what do I need? So let me look back at the problem. They ask how hard must she pull downward to raise herself slowly at constant speed. When I see constant speed, my understanding is constant speed means no acceleration, right? Then A is equal to 0. I'll put this guy 0. Now let me just go ahead and sum all these forces. So I want to assume this side is positive, this side is negative, and let's sum these things up. I have, what do I have? I have T, I have another T, let's write them, T plus T, and I have mg, but it is in the opposite direction, so I'll subtract it, minus mg is equal to what? It is equal to 0. Then it's like I can solve this equation. It's like this one is 2t. I can take that guy to this side. 2t is equal to mg. Then t is equal to 1/2 mg. If you put the numbers, let's do this. Oops. 0.5 times 72 times 9.8 is equal to 352.8. 352.8. And the unit is like, this one is Newton, this one is meter per second square. Sorry, this one is kilogram, this one is meter per second square. Then this whole thing should equal to Newton, right? Then I'll write this. B, okay, that's, where is FRW? FRW is, this is, let's look. So we are interested in the acceleration of this guy, woman plus bucket system. So let's call this woman for short. And then we are interested in the force on woman. So basically we are only interested F, woman by other things, other. So FRW, this guy is acting on the rope and it is acted by woman. So I don't care about this then, okay? Is that clear?
Sir, could you explain that again?
So remember, okay, maybe I can bring up that example. So Michelangelo's assistant, do you remember this one? So he was saying that I pull the sled with force. Basically, this is force on the sled by the assistant. This is the force. And this is going to move the sled. And he's saying that there is Newton's third law. Whatever I push, there's an equal and opposite force, which is F on assistant by the sled, this force. The key here is these two forces act on different objects. So we have to separate these different objects when we solve the equation of motion. This is what we do here. We come here and we separate, okay. We separate rope and woman system. And we are only interested in the total force acting on the woman. So this force is there, but it is acting on the rope. That's not our system. Action, reaction pairs act on different objects. So I only count the forces acting on this guy. And if I look, it is T here. Okay, maybe I can zoom. T here, T on her hand, and mg down. And this force is acting on the rope, not on the woman. So I got rid of this. Maybe I can go ahead and solve part B, and then you can think about this a little bit further. Okay. Part B. If she increases this force by 15%, what will her acceleration be? And assume the mass of person plus bucket is 7. Okay. Now, what does this mean? They say if she increases this force, okay. So this is the force she applied, right? Force applied on rope by woman, which is down, and its magnitude is 352.8 Newton. And the problem is saying, if she increased this by 15%, what happens? If this one increased by 15%, this one also will increase by 15%. I know this because for every action, there is an equal and opposite reaction. If this increased by 15%, this will also increase by 15%, right? But her gravity will not increase by 15% because it's fixed by her mass. There's nothing she can do about this. Then let's put these equations. So 15% means 0.115 T. So this one increased. Plus 0.115 T. Okay. This one also increased. And minus mg. Now, we don't know if it's zero, right? This is m times a. And our problem now is what is a? Because we already know this. T is solved here. So this means 0.15 times 2 times T minus mg. But T is equal to 1/2 mg. So let's put this guy in. Oops. T is 1/2 mg. So these twos nicely cancel. Then this is equal to mg parenthesis oh, actually I made a mistake. So she's increasing. She's like, okay. An increase is like what? It's increasing is, there is the original plus, like original T plus 0.15 T increase. That makes 1.15 T, right? Sorry, I messed up. So the same guy here. This is also 1.15. Then this guy is 1.15 mg 1.15 minus 1, which is equal to 0.15 mg, but this is equal to m times a. And I know these m's cancel. So a is equal to, oops, a is equal to 0.15 g, which is equal to 0.15 times 9.8 meter per second square. Let's calculate this. 15 times 9.8 is equal to 1.47. 1.47 meter per second square. Okay, this is one. This is another one. Yes, 1 point, yeah, okay. So how FWR pulls her up? So yes, that's fair. So imagine you are here and you are pulling. And if I pull, I'm pulling down. This is the force. This is the force I put on the rope, which is down. That's the pulling action. Is there any problem here? Do you agree when she pulls, she puts a force on the rope? Let me just give you a second to answer. Yes, good. Now I appeal to Newton's third law. Newton's third law says, okay, maybe I can do it like this. I can put two objects in contact. There is this woman and there is this rope. I just put a diagram because they are in contact. Of course, the geometry is a little different, but don't mind that. Now, Newton's third law says, for every action, there is a reaction. So we agreed on this. So there must be an equal and opposite reaction. Then I just write this, like equal and opposite, and I identify it as FWRT. So it's equal and opposite. That's also good, right? So we'll come to that. So do we agree that there is an equal and opposite T for every T. Okay, good. Now, the next step is this T is acting on woman. This force, which is up, is acting on the woman. Do we agree with that? Okay. And also, the other force is acting on the rope. So FRW and FWR are acting on different objects. So we are done with here. Now there is a pulley and there's like a tension here, right? Then there must be the same tension here. Now when I come to here and look at the tension, let's delete this guy. When I come to here and look at this tension here, I ask myself, in which direction does this tension pull the bucket? I think it's not confusing to say that it's in this direction, right? We carry things with ropes, and ropes are generally pulling things they are tied to up. And the magnitude, if this is a pulley, if this is T, this must also be T. And finally, I think there's no confusion about mg, so I just write it down, and I just sum it up. There is T plus T minus mg. No, it's, of course, we have to take the same T into account because one is acting on the hand, the other is acting on the bucket. These are different forces. So maybe I can ask this way. I don't like that way, but I think I can do. Imagine there is another string here. What should the tension be here? And it is like tied to the ceiling like this. What should the tension here be? Here. 2T, or forget about T, what is the total mass that's hanging on this guy? What is the total mass hanging on this guy? No, they just close it. Everything internal is internal. We don't mingle with internal affairs. We just look at, like, we just put like a box here and we say, what is the external? The only external is this T, and the only other external is total mg down. Then I can say, okay, this T must balance the only mg. So this one must be mg. And I say that, okay, this mg is divided into two branches here. Then one branch goes to here, the other branch goes here, and they equally divide themselves. So T plus T, okay? So basically mg is, here is 1/2 mg, here is 1/2 mg. If you are confused, you can think this way. But I don't like this way. But I think the way we initially set the equation up, sometimes it's, I think it's a good thing. Sometimes your result may conflict with your intuition. And at that point, ask yourself, did I do any logical mistakes? So right now, we have like a conflict with our intuition and say, okay, this is it. Is there any logical mistakes? And I challenge you to look and find a mistake here.
Is it possible that you could repeat the last thing you just told? I couldn't quite understand.
So which last thing?
The one with the T pulling all the system and then 1/2 separation and stuff.
Yes. Here, that's another way I convince myself this result is correct. So I imagine, okay, this pulley is like in the picture, they don't show where it is fixed to, but I imagine, suppose this guy is like tied to ceiling like this. There's like another rope, a thicker rope, strong rope, and this one is tied to a ceiling like this. And I ask myself, what is the tension here? This, I don't know. Let's call this T prime, okay? T prime. What is the T prime? And I look at the system T prime X, the system X on this red box I just draw. And I need to count all external forces on that box. I don't care about internal things. And in this red box, the only other external thing is mg going down like this, right? Mg is going down, and that's, so 1 mg is like this, and t is going up like this. Sorry, t prime is going up like this. Then I say, okay, t prime must equal to mg. Now I think I'm very confident because there's no other thing. So I convince myself T prime is mg. So I need to go one more step. So if T prime is mg, what is T? These two guys. So this T prime is divided into two different guys, right? If I look at this point, if I identify forces on this point, one T prime is up, two T primes are down. And I say, oh, okay, this T prime must be divided in two branches. Half here, the other half here. So then T is equal to 1/2 mg, okay?
Okay, thanks.
So sometimes I think it is okay to be uncomfortable with the results we find. Just keep that in mind and give it a little bit time, okay? It is going to settle by itself. I mean, don't just forget about the problem, but come back to it. Let your brain process what you saw. And maybe in like a day or 2 days, you will look at this again and you'll say, oh, okay, it's so clear. Maybe on Monday, so we are meeting on Monday, right? Monday, we can bring back this question and ask if you guys have any problem to talk a little bit more. So let's go to this guy. So determine a formula for the magnitude of force F exerted on large block MC, so that the mass MA, this guy, does not move relative to MC. So ignore all friction, there is no friction. Assume MB does not make contact with MC. Assume MB, this guy, does not make contact with this, okay? Okay, let me give you a couple of minutes. Just look at it and tell me what you think. Number one, okay, what is difficult? What is difficult? Okay, write 1 or 2 things and let's see what is difficult. Establishing the relation between MA and MB. MA and MB, okay? So one relation between MA and MB, okay? So we have to be careful with this then. Okay, this is one thing. What else? Also confused if MB will make an angle. Angle of MB. Okay, that's one thing. Anybody else? How many people do we have here? Let me see, we have 95 people. And nobody wants, okay. Impact of F on object, okay. So impact of F on MC, or okay, the way solution is. So the solution I think is not long. I think we'll see. Okay, let's start, okay? Let's go ahead and start. So first I look at F, and this F should push. So if you were the one who is pushing, what is the total mass you should affect, right? Definitely MC, right? And MC should move, and the problem is MA should move and MB should move, right? Basically, this whole thing should move. Then this F is going to affect all masses. So let's write this. So Newton's first law is, okay, F x is equal to M total times A, right? and F magnitude is equal to A plus MB plus MC times A. This is our first equation. So what else do we have? So let's look at MA, this guy. So clearly that guy is simple because there's only one thing here, and it is the tension. Of course, there is like mg and there's like normal force, but it's in the opposite direction, so we don't care about this. We are only interested in horizontal direction. Then I say T is equal to MA times A. Okay. And the tricky part, MB. So let's zoom in to MB and see. So there is T. Now, this T has like two components. One, this Ty, and the other is this Tx. So I ask myself, what is the function of Ty? What does Ty do? And I think Ty, all it does is balance here, mg. Otherwise, this whole thing would fall, right? And what does Tx do, this guy? I think it is going to give acceleration. So let's write these two equations. So first one, Fy is equal to 0 because there is no motion like here. And this one gives me T, okay, what is Ty? I want to call an angle, like let's call this theta. And Ty is T times cosine theta. T times cosine theta is equal to mg. Now I write the forces for x direction. Should be 0. No, not 0 here because it's moving with the same velocity, which is mb times a. Then t, what is tx? T times sine theta is equal to mb times a. So what are the unknowns? I know these guys, MA, MB, MC given. A, I don't know. And F, I'm looking for F. So if I find A, I'm done. But these three equations, there are how many unknowns? MA is known, T and A are not known, theta is not known, MG is known, MB is known. So basically, if I look at this equation, unknowns are T, theta, and A. So I have to eliminate. And I want to, for example, how can I eliminate at least one unknown? For example, how can I eliminate at least one guy here? For example, can I eliminate theta? When you look at these two equations, what do you see? Any suggestions what we can do? Tangent theta. Okay, that we can do. Any other suggestions? Square. Why? Why should I square? That's not. Squaring generally makes things complicated, right? Why would I square? All right, so that's it, yes. So if I square this one, I have t squared cosine squared theta equal to m squared g squared. Now if I square the other one, t squared sine squared theta is equal to mb squared a squared. And if I sum these guys, I have t squared, open the parentheses, cosine squared theta plus sine squared theta is equal to, so this m is, I think, mb, I forgot, sorry, mb squared a squared plus g squared. But we know from high school analytical geometry, this is 1. right? Now I have two equations. T is equal to MA times A, and T squared is equal to MB squared A squared plus G squared. So if I square this guy, these two guys should be equal, right? Then T squared is equal to MA squared A squared from here. And this is equal to MB squared A squared plus G squared. Can I solve this equation for A squared? Yes, I can. MA squared minus MB squared times A squared is equal to MB squared times G squared. Then A is equal to MB times G divided by MA squared minus MB squared. And what did we say in the beginning? If we know A, we know the force. Then let's put this. Then force is equal to MA plus MB plus MC times MB times G divided by MA squared minus MB squared. So that's our final result. Okay. Any questions here? So does anybody have any questions about problem 59? So I suggest you don't just forget about these problems, okay? Come back to these. Okay, I'll end polling and then publish the results, share results. Now let me see what if MA moves relative to MC? In this case, T is equal to F because MA is not moving. Let's look with, in this case, T is equal to F. T is actually not quite F, right? Here in this case, T is equal to MA times A. And if you put A, it's actually T is equal to MA times MB divided by MA. Okay, let's write this. I just put this guy in, maybe. T is equal to MA times MB divided by MA squared minus MB squared times G, which is kind of nice, right? And MA is actually moving, but MA is not moving with respect to MC or MB. So this whole system moves in a unity, like a one piece. So that's like a fragile balance. And that's the condition for that fragile balance. So what if MA moves relative to MC? Exactly. If MA moves relative to MC, that means T would be different. So we have to know something about how much it moves, or the problem should give us something about that, right? Or if you increase the force a little bit and break this balance here, maybe MC is going to move faster than MA and you will slide back. So there are different possibilities that can make it more and more complicated. T plus TX question mark. T plus TX question mark. I'm not sure what this means. So I think it's a good point to stop here for today. So I'll end the lecture here and you guys are free to go. I'll just answer the questions, okay? Thanks everyone for coming. I'll see you on next Monday.